This is part 1 of Unit 5, Lesson 4, Concavity and the Second Derivative Test. In our last lesson, we used the first derivative test to find intervals on which the function was increasing, decreasing, and whether or not those increases and decreases led to a relative max or relative min. So now what we're going to do is see that the derivative of f prime, or the second derivative, will describe the concavity of the original function. So concavity tells us the direction of the curve, how it bends. Like, is it bending out? Is it bending in? And concavity has places where it changes direction, and those places are called the inflection points. So we're going to start by talking about concavity in a little more detail, because we have floated this concept around, but we haven't really formalized it. And then after that, we're going to talk about the second derivative test in a future video. Okay, so what we want to do in this first exploration is we want to draw tangent lines at the points along the curve that are marked, and we want to notice what changes about the slopes of the tangent lines as you move from left to right. So drawing a little tangent line here, we can see we're going down, then we're going up, we're going up, we're going up. Okay, we're going up, then, whoops, it's completely missed there. And then on the other side, we're going down. All right, this is harder to do on a screen than it is on a piece of paper. We'll just pretend that that's this line. We're going down, we're going down, we're going down. So what you want to notice is that as you go along, the lines are getting, in the first graph, the tangent lines are getting steeper, so f prime is increasing. And on the other side, what we notice is that f prime is decreasing. It's getting more steep, so it's getting more negative. Okay, we're going to use that to help us when we go to use our derivative test, that idea. Okay, so here's our formal definition of concavity. Let f be differentiable on an open interval I. The graph of f is concave upward on I if f prime is increasing on the interval, as we saw in the first picture. And f is concave downward on I if f prime is decreasing on the interval. So here's how we test for concavity. If f double prime is positive, then we're concave up. So we have this shape. If f double prime is less than 0, then the graph of f is concave down. Now we're going to start applying this idea. Okay, example 1. Given f of x is 1/3 x to the third minus x, determine the open intervals on which the graph is concave upward or downward. State the point of inflection. Explain how you know. Okay, so what we're going to see is that we're going to have to take the derivative twice. So we're going to take f prime of x, and we're going to get x squared minus 1. And then if we take the second derivative, f double prime of x, we get 2x. And then to find the inflection points, the possible inflection points, we set this equal to 0. So right now, we're saying that x equals 0 is a possible inflection point. We're going to talk a little bit more about that in subsequent examples of why it might not be. Okay, so we're going to do a sign chart like we did before. And so we're going to have the direction of f, the sign of f double prime this time. And here are x's. We have 1, 0 here. And if we choose a point on the left of 0, like -1, what we'll see is we substitute that in the derivative, we get a negative. So a negative second derivative means that we're concave down for f. And on the other side, if we use 1, and we'll get a positive number. So a positive second derivative tells us that we are concave up. Now, just a little side note here, if we look at our second derivative, our first derivative, which was x squared minus 1, and we set that equal to 0, we can see that we have two critical numbers, which are -1 and 1. So it does make sense that we would have a change in the concavity of the graph between the critical numbers. Okay, so what are our conclusions? We can say then that f is concave down on -infinity to 0, since our second derivative is less than 0. And our other conclusion, f is concave up on 0 to infinity, since our second derivative is positive. Our third conclusion is that we can say that x equals 0 is an inflection point. And how do we know this? F double prime changes sign from negative to positive, and f double prime of 0 equals 0. Okay, so that's a little taste of the second derivative test. All right, next example, graphs and derivatives. The concavity of f double prime of x and the direction f prime of x of the function f of x is related to the slope of the derivative. So this is just kind of laying this out here. So if you were to look, this is the graph from our last example. So if we were to look at how this looks, so here's -1, here's 1, and what we see, this graph looks something like this. Let's see if I can draw this real nice. There we go. Okay, so what we have here, so this is our graph of f. What we have here is our inflection, our relative maximum here. Here's f prime of -1, and you can see that's a horizontal tangent line. Here is our f double prime of 0, and it definitely equals 0. And here is our other horizontal tangent line. This is our f prime of 1, and that equals 0. So you can see that inflection point there is definitely in the middle of this graph. Now, if we look at its derivative, here's what the derivative looks like. This is a parabola, like this. And here's how those points turn out. So now what you'll notice is where there's a horizontal tangent line of the derivative, that is its derivative. So here the second derivative at 0 is in fact 0. And then we can see that here and here, here's -1, here's 1. These are the zeros of the derivative, so they are our relative mins and max on the original function. So here we have f prime of -1 equals 0, and here we have f prime of 1 equals 0. And since our tangent line is going from, not our tangent line, I'm sorry, our derivative graph is going from an area of positive to negative, this is going to be a maximum. And on the other side, our derivative is going from a negative value to a positive value. That makes that 0 a minimum on our original function. So there's a little visual of what we just did. Okay, I'm going to summarize here and then stop, and then what I'll do next is I will continue with what exactly we do with points of inflection. So what I have at the bottom here is for us just to summarize this, what I just said in the description of the graph. So we have a little sign chart. So for for the derivative, so looking at this graph a little bit, let me just zoom out here a little so we can see the graph and talk about it again. So here's our graph. What we have going on here is that before -1, our derivative is positive, and you can see that on the graph here that the slope would be positive, the tangent line, and you can see it here in that section of the derivative. It's above the x-axis. So our derivative is positive, so that means our function is increasing. And then in between the two, the derivative is negative in this section, so that means the function is decreasing. And you can see that here, this section of the graph is negative. It's below the x-axis of the derivative. And then after 1, the derivative is again above the x-axis. It's positive, and you can see in the function we now have a positive slope of our tangent line. So the graph is increasing again. So a sign chart for our second derivative, looking at our derivative here, is our 0 tangent line for the first derivative. And what we see before that, the slope of this line here is negative, and that means that our original function is going to be concave down, and afterwards the slope along this side of the 0 is positive, so that means our original function is going to be concave up. Okay, so this ends the first video, and I'll continue in the next video.